All right, so in order to proceed, we are going to have to study the concept of homotopy. Gilmore now that we've sort of discussed SU2 and SO3, and I guess the quaternion version as well, we are now about to embark on distinguishing these two sets, or making hay over the fact that when we created the mappings for these sets, we got a case here where antipodal points were identified, and a case here where the entire sphere was identified. And we discussed that in huge detail for like the last 2 lectures. Now we're going to sort of exploit this fact and study it and see what's the big deal about it. But in order to do that, we have to understand homotopy. And Gilmore doesn't really dive too deep into the idea of homotopy, and yet he's working with an actually very clever example. I mean, this study here affords us a chance to really get to an interesting example of homotopy, much more interesting than the elementary homotopy you would typically learn in a quick review in a topology book. It's one of the more interesting examples of homotopy. So we're going to take this opportunity to focus on the idea of homotopy in a fundamental and elementary way in this lecture, and then apply it in our next lecture to the situation that we have and see why it's a relevant thing to know. So homotopy is actually the starting point for an entire intellectual mathematical discipline called algebraic topology. And we are not going to talk about this. This is like a lifetime of dedication. It's probably one of the most fascinating forms of mathematics that I've ever seen. I know enough about it to be like blown away by it, and we could someday do a series on it, but let's just say that we only need to proceed with the physics we want to understand and the understanding of Lie groups. We only need a certain limited degree of understanding of algebraic topology to get where we want to go. But to suffice it to say, algebraic topology takes, whenever you see algebra, you kind of can replace this with group theory. Not entirely, because there's other algebraic structures that algebraic refers to. The algebra part almost always, though, ultimately means group theory. And of course, topology is the study of point set topology. We're usually referring to point set topology. So blending group theory with topology creates the discipline of algebraic topology. Now, this is potentially very confusing given the fact that we're studying Lie groups, right? We're studying Lie groups. And what is Lie groups? Well, we've already kind of gone through this whole idea with Lie groups, that what we're doing is we're taking a group, an infinite group, right? A group that has an infinite number of sets. We're giving this group a topology, so we're creating a topology on the group. So we're turning the group into a topological space, right? And then in particular, because of the nature of the way we do this, we're forcing certain functions to be continuous, and the whole thing is a manifold. So it seems like we've already done this. In other words, we've already taken group theory, right, and blended it with topology and created this thing called Lie groups. But that's all, what's the word? It's a spurious similarity. Spurious, meaning that, yes, we've started with a group that had enough sophistication in it that it could actually be given a continuous topology, and it happened to be a manifold as well. In other words, we had a group that was so rich that we gave it it had an infinite number of elements and a topological structure that was correct to make it a manifold. It happened to be a manifold. We're studying groups that are manifolds. And it seems like that the underlying topological space happens to have a group structure. That's different than what algebraic topology wants to do. Algebraic topology says, no. I'm going to start with an abstract idea of a topological space, right? I have a topological space, and I am going to give it a group structure. Let me put it this way. I shouldn't say that, because you're not actually giving it a group structure. What you're doing is you're taking a topological space and you're going out in the world and you're discovering some group in the world that contains information about this topological space. And finding these groups that are relevant to certain topological spaces, that is what algebraic topology is all about. Now, these groups that they attach to topological spaces are supposed to be topological invariants, meaning if I take this group here and I turn it into another, if I take this topological space, not this group, because it's not a group, right? It's just a topological space. I take this topological space and I turn it into another topological space using a mapping that is a homeomorphic mapping, meaning it's 1-to-1, it's on-to, and it has a continuous inverse, right? Or it has an open inverse, right? So it's a homeomorphism, right? Gamma is a homeomorphism. Then the resulting topological space, the same group will be associated with this topological space. This is a topological invariant, which means under homeomorphic mappings, it remains a property of this space. So algebraic topology is doing something different. It's not starting with a group, giving the group a topology, identifying it as a manifold. No, it's starting with an arbitrary topological space, and it's looking for groups that apply to those topological spaces. So now when we say we're going to apply algebraic topology to our study, well, now it's really abusive. It's really confusing, right? Because the original topological space that we're going to study, that we're going to look for groups that are associated with, happens to also be a group, right? So we're starting with a topological space that happens to be a group, a Lie group, and now we're going to look for groups that can be connected to that topological space. We're going to look for new groups that have information about this topological space, which in itself happens to be a group. So that's what we're going to do today. We're going to start studying but we're going to study it down here. We're going to study it in the abstract. We're going to study how certain groups might be attached to a topological space. And then in the next lecture, we're going to apply that work to the particular topological space we're interested in, which happens to be a Lie group also. Okay, so let's begin. So we will start with an abstract topological space. Now, we always draw these topological spaces as like blobby regions in the plane. And that is a little bit poisonous in the sense that it's supposed to be a very abstract set, right? We don't know what kind of set this is, but we do know it's topological space, meaning we've applied a topology to it. So we know we have a topology. So, but otherwise this is supposed to be quite arbitrary. Now, what we do with all of these sets is we try to define the notion of a path. We have to have some way of starting at a point in the set and wandering through other points in the set in a continuous fashion, where continuity is defined by topology. Now, we've talked about paths in many places in these lecture series, and we're going to do the exact same thing we always do to define a path. A path is essentially a function. And that function is the usual thing. We're going to say a path in space is a function that takes a small segment of the real line, the closed segment from 0 to 1, and maps this segment to a points in the abstract space. And the first point, if we call this path gamma, the first point, of course, is gamma 0. And then the path wanders somehow continuously in the function space, and then the last point is gamma of 1. Now, when we talk about the continuity of this function, right, this has to be a continuous function, right? So it has to be the way continuous functions are defined is the inverse of this function has to be open on the real line. But when we talk about that, we end up talking about the topology on this line, which is induced from the topology of the set. So if we use our metaphor of, this is an open set, open balls, we use sort of the open ball metaphor on this blobby space, right? Then the intersection of that open set with our path would be this little strip here, and that would be the open set whose inverse that would be the the open set whose inverse has to be open down here, right? And then this gets the regular topology. This is, remember, R, that's just R, and it takes the regular topology, the topology where all of the open intervals down here, open intervals down here are considered open sets in the topology on R. So I guess there's the regular topology of the real line. So when we talk about gamma inverse, we're talking about taking these open sets on the line, which are the induced topology on the line, induced from the open sets from this topology. So it's the intersection of the open sets of this topology with our subset. Remember, the line is a subset. This line is a subset of our space, right? So any subset of a topological space can get the induced topology by taking intersections of the open sets of the topological space with the subset. And that's what this little red piece is. So if we take gamma inverse of this little red piece, we better be open on the real line, and that is and that's what it defines a continuous function, gamma. Now, once we understand the notion of paths in a topological space, we can create two sort of topological invariants. We can create a topological invariant. I guess what I'm trying to say is there are two topological invariants that are associated with the notion of connectedness. The first, and the one that we're most worried about, is called path connectedness. There's path connectedness, and then there's just, I guess, connectedness, right? Then there's just connectedness. Regular old connectedness is the kind of idea where the total set is actually the union of two disjoint subsets. If the total set X is actually this component A union this component B, we say it is, and the intersection, and A intersection B equals the null set. So I guess X equals A union B, A intersection B equals the null set. And A and B have to be open as well, but they're also clopen, right? Because if A is open, its complement must be closed. So B is closed. But if B is open, then A is closed. So they're both open and closed. Anyway, the point is that's a disconnected set, if you can find two sets A and B like that. We're always presuming that we're dealing with a space that's connected in this sense, that you cannot split it into A and B like that. So we're dealing with a connected space. The other way of understanding connectedness is this idea of path connectedness, which essentially means that I can take any point in the set and I can find some function gamma that will connect me to every other point in the set. So if I wanted to go to this point, I could find a path from that point to there, and if I wanted to go to this point, I could find some path that would get me there, and these paths can cross, right? The point is I can always connect every point together with a path, and a path is defined very specifically as a function that starts at 0, goes to 1, and the path is continuous, and it goes through the space. Now, there's a lot of interesting topology about how path connectedness does not always imply, connectedness in the original sense that I just had, in the first sense, right, with two disjoint sets. The two aren't always the same, right? You can sometimes have disconnected set, or a set that's connected in this sense, but not path connected, right? I think that's how it goes. And there's these dysfunctional sets that do this, the most famous being something called the topologist sine curve, which is really, I think, sine of 1 over x, right? Something like that. And you can go through all of that. We're not going to cover it today. We're dealing with things that are path connected and connected in the regular sense. But path connected is what we're after. So we're going to presume that we do have a path connected set, and here's an example path, and this is the definition of a path. So the next step is to talk about different paths between 2 points. And this is where we now start to create the core essence of the fundamental group. The first idea is to sort of understand how this notion of creating paths inside a topological space can lead to an idea of a group, right? And so the idea is that if I have this path here, right, and say I have another path that starts here and goes to a different point, for example, a path like this blue one, right? This blue path, if it's a path, so it must fit this definition here, right? So it starts at phi 0, which is equal to phi 1. It goes to phi 1. So now I have this path. I guess I should draw its little arrow to show that it's the function phi. And so now I have two paths. But notice the two paths go from, ultimately, if I traverse one path and then first this path and then this path, it looks like I have a path all the way here. And that's true. However, technically, our definition of a path goes from 0 to 1. So when you study this in books, what they do is they spend a lot of time reparameterizing this path so that you ultimately create a whole new path, which they might call lambda, right? Which goes from 0 to 1, but lambda 0 is here, and lambda 1 is all the way over here, and the path traverses twice as fast or something like that. But the point is you can combine the path, any path gamma with a path delta, as long as they both share the same, the endpoint of one is the beginning point of another. So in this way, you can combine paths. So you would say that lambda somehow more or less equals phi after gamma, where this is the traversing of gamma and then the traversing of phi, and then you can end up creating a point lambda. Now notice you can't really take any two paths between any 2 points and do this operation, right? You really have to make sure that the paths have these sort of endpoints kind of together like this, right? But the notion of adding paths or combining paths or multiplying paths, but basically taking two paths and producing a third path, that's out there, right? That exists. You know, you can create this path lambda from two paths gamma and phi. But if I tried to say something like, oh, well, the set of all paths must be a group, that's not really true, because I can have, you know, a path over here, and the logic I just used can't be used to combine this path with this green path, right? Because they don't really share the endpoint. You would have to say, I'd go follow the green path, but then I have this discontinuous jump over here, and any function I made that mapped the real line into a path that does this and then boop, that, it wouldn't be a continuous function, right? And then, but a path has to be a continuous function. So the combination of this green path and that red path isn't a path. So I can combine some different paths, but not all different paths. So I don't have the ability to turn the set of all paths that exist on this set into a group yet. But I do know a way of combining at least some of the paths. So I'm onto something. Okay, so keeping that in mind, let's understand the notion of homotopic paths. All right, so now this whole plane is going to be inside the set, right? So I'm no longer going to worry about, oops, that's for later. I'm no longer going to be worried about, you know, sort of segmenting off the set. This entire picture here, we're dealing with the set X, which is a topological space. So we've got X and its topology. So, and I'm no longer worried also about displaying each of the paths with its attendant domain, right? This would be the domain, and this is sort of the range of the path. I'm not going to do that. When I draw a path, you presume that it's a continuous function from 0 to 1 off the real line. So we're there now. So I've chosen a point that I'm going to call gamma 0 and a point that I'm going to call gamma 1. And I'm going to call this the path. This is a very standard picture. You'll see it in a million different books. But I'm going to call this the path gamma. So that's the path gamma. And the parameter for gamma will be, let's see, I think S and T are pretty common. So I'll go with T. Whoops. Oh, no. I'll go with gamma of T. And the reason we do T is we're just going to sort of lean on this idea that, hey, as time marches on, you move along this path, right? That's time, right? So, you know, it's any parameter, however, but t goes from 0 to 1, and as time progresses from 0 to 1, you're somewhere along this path, right? That's sort of the way to think about that. Now, the point is, of course, is that there are many paths that connect gamma 0 to gamma 1, right? And we can create another such path. And here I've done it. I've created the path phi. And phi of 0 equals gamma of 0 in the sense that they both are the same point in the topological space X. Phi of 1 and gamma 1 are the same, so I could actually put little equal sign there, right? But it's clear that if for phi of t, and I'll use the same parameter for phi, right? Phi of t is clearly not equal to gamma of t, because these are totally different paths. Now look, these are totally different paths, but had I drawn this path like this, right, there would have been 2 points where phi of, say, t1 equals gamma of t1. And likewise, there phi of t2 would have equaled gamma of t2. That's okay. Paths can intersect. They're still different. They may be the same at a few points, but that doesn't affect this argument about what we're talking about. It's just cleaner and easier to have 2 totally separate paths, but you don't have to have 2 totally separate paths. Meaning you can have paths in principle where phi and gamma intersect. You don't want them to be the same path totally. You'll see why in a minute. Okay, so with this in mind, with I have 2 paths in gamma 1, gamma c, I want to create a homotopy. A homotopy. And like almost all things in this story, a homotopy is a function. So the idea of a homotopy is, as I said, it's going to be a function, but ultimately what we want to be able to derive from this function, what we want to learn from this function is a collection of different paths that really morph. They're sort of intermediate paths that take gamma and slowly, in a way that we'll define very rigorously, in one way or another, they've eventually become phi, right? So each of these red lines is part of a collection of paths that, in an intuitive way, start with path gamma, and slowly each path becomes a little bit more similar to phi. Now that's because this homotopy is very pleasant, right? It's doing the obvious thing. It's sort of starting at gamma and it's becoming phi. However, a homotopy is just a collection of paths where the first one is gamma and the last one is phi, and that first and last is very rigorously defined, as we will do in a moment. But in principle, it doesn't have to necessarily approach phi right away. You could almost imagine, a homotopy that sort of starts by going, these paths, and it gets worse and worse from phi, but then it starts to reverse itself and it becomes phi. It doesn't have to be this beautiful, smooth progression from gamma to phi like you see in most demonstrations. It's just so much easier to picture that particular homotopy than this nice, convenient homotopy is much easier to picture. But the point is it's any collection of paths where the first one is gamma and the last one is phi. But what do we mean by first and last, and how do we make this rigorous? All right, so we have to define a function that is a homotopy between gamma and phi. That's the language. We're looking for a function called a homotopy between gamma and phi. All right, so to make sure that we understand sort of the boundaries of how this function has to be constructed, one of the things I implicitly made evident, well, let's see, I made it evident at least, that gamma and 0 and phi 0 were the same point, and gamma 1 and phi 1 is the same point. We're going to enforce that as a requirement for this function, right? It is completely plausible to talk about the homotopy of the function gamma with, say, this function here, which I might call lambda of t, right? I can easily describe the homotopy like that as long as I allow the endpoints to move as well, as long as I create a family of curves where the endpoints are also moving, right? So this family of curves might describe some sort of homotopy between gamma and lambda. And doing that is far less interesting. it's far less interesting. It'll become clear later. So we're more interested in something we might call a fixed endpoint homotopy. Sometimes it's called FEP, fixed endpoint homotopy. So that's the first rule we have, is that the endpoints of these things are the same. So with that in mind, I'm going to create a function, I guess I'll call it H, right? And H is going to be a map, and it's going to be a map that goes from the interval 0, 1, Cartesian product, the interval 0, 1, and this is a very formal construction, into the set X, right? So remember, this whole thing is X, right? This is the set X. This is the abstract algebraic set, right? It's this thing here, right, that we talked about earlier. And 0, 1, 0, 1 are two little intervals on the real line, right? So, I would have one interval from 0 to 1 and another interval from 0 to 1. One of those intervals was going to be t. It's going to be the same t that drags us from the initial point to the end point, right? Each of these curves is going to be parameterized by t. But I need a way to select the curves, right? So selecting which curve, I'm going to define the curve associated with the point 0 from this other parameter, right? This might be, we'll call this one here this will be the t parameter. And I'll call that the S parameter. S for selection, T for time. How about that? Remember, time is very abstract here, right? It's not literally time. There's no physics in any of this, right? That should go without saying, I guess. So this will be S. And as S starts at 0, we define this black curve. And then when S is 1, we're talking about this green curve. And any intermediate value of S defines some curve in between. So the S selection sort of moves this way along the curves. So you can imagine if I pick a value of t, say t1, and fix it, then S equals 0 will define this point, and S equals 1 will define that point, and any S in the intermediate stage will define these various points along these various curves. So S really selects the curve. So now when I look at H takes two parameters, S and T, and it's got to be such that H of 0 of T equals gamma of T, and H of 1 of T equals phi of T. Now, phi and gamma already have their rules enforced, where we know that phi of 0 equals gamma of 0, and phi of 1 equals gamma of 1. So that's the fixed endpoint principle, right? So that's enforced in our definitions of phi and gamma. But the homotopy, which is a map between 0, 1, Cartesian product 0, 1 into X, we are defining that when S is 0, we're dealing with this gamma curve, and when S is 1, we're dealing with this phi curve. And all these intermediate values of S are going to have to define continuous curves, continuous paths. I shouldn't say curves, I should say paths, right? Because paths implies all of this architecture, right? This is what a path is. It's defined by this. A curve, that could mean anything, right? So this H really defines an infinity of paths that all go from all go between these two endpoints that morph gamma into phi. So the point is the language that I'm after here is that the curve gamma is homotopic to the curve phi if I can define this function, which, by the way, has to be a continuous function. This has to be a continuous function from this Cartesian product space into X, which is going to forbid any breaks in this curve. So The endpoints are the only 2 points that are fixed, by the way. And everything else is, as long as you can find such a function, gamma will be homotopic to phi. So that's the definition of a homotopy, is finding that function. Now, what we typically will do is, to describe it, we'll create this space here, and we'll kind of study this 0, 1 cross 0, 1 space. So what you can imagine now is imagine the square, right? T 0, 1 here and S 0, 1 here. And this is a good representation of 0, 1 cross 0, 1. Remember, this simply represents ordered pairs S and T, right? That's what a Cartesian product is. It is the set of all these ordered pairs. So we take all those ordered pairs, we just kind of lay them out in a 2D grid, like so. So now we're talking about H is a map from this set of ordered pairs into X. So it's a map from this square into the space X, which is on this plane of the board, right? And now I know there's this weird thing where I've drawn the space in the same plane that I claimed as representing the total abstract space. So I guess now, to be technically correct, I have to sort of split. Oops, let me choose a different color, blue here, right? So this is the set X with the topology of X. Let me make my T a little better. The topology of X. Everything on this side of the blue line, right? And this represents the domain, and this is now the range is over here. Okay, little technical matter. So this part of the domain, this line between 0 and 1, when S equals 0, right? So this piece of the domain, I'll do it in black. I'll bold it out. That piece of the domain, right? That maps onto this line gamma, right? That's S equals 0, T goes from 0 to 1. So as I move along this line here, that becomes the parameter that drags me down gamma. And then this piece, say halfway, right? That piece of the domain, that drags me down, say, this curve, right? Say some curve that's sort of halfway. We'll assume this is behaving very nicely, not like one of the ones I talked about earlier that gets worse and then better necessarily. This is maybe this middle one, right? That might be the S equals 0.5 curve, say. And then, of course, the this top one here, that one I can just do in green straight up. Actually, I guess this one should have been red, right? That one should have been red. And then this one here is green because it corresponds clearly to phi, the green curve. So that's the typical way of looking at how a homotopy works. You can likewise go vertical, right? I can look at, say, this middle curve. I'll start with the middle one for the vertical, and that might be actually this blue line that I've drawn here, right? Where T is constant and you're moving from curve to curve to curve to curve to curve. We actually did a little bit of this if you did the general relativity course. When we studied Riemann curvature, we had a little bit of an analogous kind of analysis between geodesic curves in space-time. Of course, this is very abstract math, unrelated to that, but we did draw this notion of having one parameter choose a path and then another parameter chooses where you are on the path, right? And that's exactly what T is. T is where you are on the path, and S selects the actual path you're on. But what's really interesting here is this line here, right? That is the constant map that only maps to this point, right? When T equals 0, every one of these paths starts at that point. And when T equals 1, every one of these paths has ended at this endpoint here, right? So those two, these are constant maps, right? The mapping from this subset of the domain into the range is a constant map. Okay, so that is how we define homotopy. If you have two paths that you can create this kind of function between them, you have homotopic paths. Now there is another notation that can be used that's kind of convenient. I can always put this S parameter that's here. I can put it as a subscript, and you often see that. So h0 of t equals gamma of t, and then I can write h1 of t equals phi of t. And now each version of h represents a separate path. So you would have h.5 of t, right, is a path. And you have to subscript it with a real number between 0 and 1, which is kind of annoying. We're not used to seeing subscripts with real numbers. But it gives you a little bit of a feel that you're now dealing with a path because you only have one parameter there. You've kind of taken this, you've taken the parameter 0 or 1, or you've taken the s parameter. I guess I should write it out here. You take, you know, h of s of t, and you write it instead h of s of t. And this looks more like a path. So that's a little bit more of a convenient way of doing it sometimes. I stick with this. It's this exact same thing. It's purely, I guess the word is, it's purely symbolic, semantic. It's just a choice of how you want to display it. But this really emphasizes that you're dealing with a family of paths, and that family is h of s. That's a collection of paths, an infinite collection of paths. And if you're dealing with a fixed endpoint homotopy, then it's a family of paths connecting two paths, that the two paths h0 and h1, right? So you kind of get rid of the gamma and the phi, and you can say, oh, h0 is connected to h1 through the homotopy h, and the subscript there would go through every real number between 0 and 1. So that's probably another way of looking at it. We're going to stick with this. Most books use that notation. All right, so I've rewritten this homotopy in a very sort of streamlined form. I only have one representative homotopic, intermediate homotopic curve. Gamma, I'm leaving off the implied index t. Phi, I'm leaving off the implied index t, but I'm showing you how it relates to the actual homotopy h. All right. So now I just want to run through some really quick and obvious ideas. First thing, I'm going to write gamma, gamma is homotopic to phi. Gamma is homotopic to phi because we have found a function h, which is a homotopy. Now, we've done this abstractly, but in principle, we've found a function h that connects gamma and phi, and it's continuous, and it's it follows all the definitions that we described here, right? So gamma is homotopic to phi. Now, because gamma is homotopic to phi, it's very important to realize that phi is homotopic to gamma. Now, this seems obvious, but because we have a homotopy from gamma to phi, you have to kind of show, are we sure that there's a homotopy from phi to gamma? I have to create a new function where as s goes, remember, s has to go from 0. When s is 0, that's the first curve. When s is 1, that's the second curve. So I need to find a function where s is 0 on the green curve and 1 on the black curve, right? And that's not hard, right? Because I just defined a new homotopy, f, which f of, say, 1 minus s and t, right? So I'm using the same s, and then I replace 1 minus f with lambda. So I say lambda equals 1 minus s, and then I create f of lambda and t, right? And now f of 0, f of 0 of t is really the same thing as h of 1 minus, is really the same thing as h of 1 of t, right? Because I'm now defining lambda to be 1 minus s. So the point is I can make a very, very trivial substitution of variables, and I can find a perfectly defined homotopy as we've defined it here, right? As we've defined it here and on this slide, I can find a homotopy between phi and gamma. So this means it's reflexive, right? And you can see where this is going, right? I've shown reflexivity. And whenever you show reflexivity, what's the next thing you're going to show? Whoops. It's not reflexivity. Sorry, it's symmetry, right? I've shown symmetry. Symmetry, right? Reflexivity is showing that gamma is homotopic with gamma, right? Well, that's easy to show. I can create a homotopy between gamma and gamma, and it's just the constant function, right? It's the function where nothing changes, right? So this is reflexivity. Sorry, it's reflexive. So once I show symmetry and reflexivity, you know that the next one to show is transitive, right? Transitive, meaning if gamma is homotopic to phi, and if phi is homotopic to another curve, which say I'll call that one gamma phi, I'll call it mu, right? So if gamma is homotopic to phi and phi is homotopic to mu, it better be true that gamma is homotopic to mu, right? And that is not hard to show because if mu, remember, everything's fixed point homotopic here, right? So if this is mu, right, and I have that phi is homotopic to mu, that means there's all these curves like this, right? So now I just do the same game with gamma and mu, and I go through all of the curves that connect me to phi, and then I add the curves that connect to mu. And what I have to do is I have to reparameterize S so that, because now I have h of 1 of t equals phi, I need to find a new homotopy. I'll call it G, where G1 of t equals mu and G0 of t equals gamma, right? And that's not hard at all because I just sort of double the speed, right? I basically, the new parameter, maybe I'll call it eta, right? The new parameter will go, eta will equal 1/2 of S, right? And so, and then, no, I think it's wrong. I think eta equals 2S, right? If eta equals 2S, then when S equals 1, eta equals 1/2. So I can write, G of eta and t, and now when I get G of 0.5 and t, that's going to equal H of oh, no. I was right the first time. Eta will be 1/2 S, right? So when S is 1, you're at H1 of t, which is phi, but eta will only be 1/2. So G of 0.5 t is going to equal H1 of t of phi, and then after that, for numbers larger than 0.5, then G is, so this is the definition, G of, yeah, I guess the way we write it is like this. Hold on, let me rewrite this. Yeah, I think this will work. Right? So G of eta and t is H of 2 eta and t when eta is less than 1/2, and then it's F 2 eta minus 1 of t when eta is between 1/2 and 1, right? So if the first homotopy H goes between gamma and phi, right, then when eta is 0.5, right, so G of 0.5 is going to be H of 1t, which is gamma. So that gets us to gamma. Then if F is the homotopy that goes from gamma to mu, then F of, then for the second half of eta's run, right? So eta's now 0.5 gets you halfway. So say eta was 0.6, that would be 2 times 0.6, which is 1.2 minus 1, which is now F of 0.2 in t, which is some curve between phi and mu, and ultimately this G now defines a curve that goes between 0, eta goes between 0 and 1, and gets you all the way from gamma to mu, okay? So the point is you're transitive, right? You're transitive. This actually applies because given these two homotopies, you can always produce that homotopy. So the fact that it's symmetric, reflexive, and transitive in the case of fixed endpoint curves, which is the ones we care about, we now have an equivalence relationship. Curves that are homotopic to each other form an equivalence relationship. And that's really critical because when it's equivalence relationship, that means we can take all the curves, all the possible curves, right, that start at the same spot and end at the same spot, all the possible paths, all the possible paths in this space X that do that can be divided into a partition of equivalence classes, and they're equivalent by being homotopic. And that's really important. Now, the way we've drawn this, of course, doesn't inspire much fascination because what two paths would not be homotopic, right? I already said that paths can intersect, so if I came up with some random weird path, like, say, a purple path here, say a purple path that did this, you can't really see that purple very much. Oh, wait a minute, hold on. A purple path, right, that did this, you know, that doesn't matter, right? We can still define homotopies with strange paths. Doesn't matter. The path could go around like this and loop and loop and loop and come back there. That's, you know, still a path, right? So what gives, right? What's the deal? I mean, all paths seem to be homotopic. So in the next lesson, we're going to talk in a lot more detail about this, but this is the whole issue here. If I take this space, right, here's a space inside this is now this is now literally a piece of the plane, right? So this isn't some abstract set. This is literally a piece of the plane. It's a disk, but it's missing this part of the disk, right? This disk it's an annulus, right? There's a missing piece of the disk. So the idea is that if I picked a point inside this set, say that point, and then I picked another point inside this set, right, like that, I can define a path between them, right? I use the very same mathematics as always, and we define the path between those 2 points. Now you can kind of see where homotopy is a big deal, because if I look at another path between these 2 points, say this purple path, right, the homotopic paths between this purple path, you know, these homotopic paths here, right, or say this one here, that's all homotopic, right? All of these fixed homotopic paths have to go around this gap in the same fashion. I cannot choose a path that goes this way, because that path cannot be continuously deformed from you cannot continuously deform this original black path into this red path. This path is not homotopic. You cannot define the function we need to go continuously from this black path into this red path. Can't be done. And so this set has at least 2 different equivalence classes, right? That this red path is homotopic to this blue path and all of these blue paths, but it's not homotopic to any of the brown paths or the black path. So there's at least 2 homotopies or homotopic equivalence classes for this particular set. And that's an important fact. In fact, there's an infinite number of separate homotopic sets. And that should be evident from the fact that I could depart this point, go around the center once, twice, 3 times, and then land at, or maybe 4 times, right? And then land at the final point. And that path would be homotopic to any path that also goes around the center 4 times, right? And, or I might have a path that just goes around the center once. Those 2 paths, the blue path and the red path, are not homotopic. But the red path might be homotopic to, let's redo the red path, right? The red path goes around once, right? That path is not homotopic to this blue path, right? You can't continuously deform the blue path into the red path. And that path is not homotopic to, say, this black path, which goes around twice, right? So I have an infinite number of equivalence classes that really count the number of orbits around this annulus. So it's not a trivial thing, right? It's a trivial thing when you consider the space in this very abstract way, and you draw these sort of lines in the plane, and you say, oh, you're defining homotopy. Yeah, it does. It looks, because the space, the implied space here is just the plane, so it's very, very obvious what's going on, and it seems like, well, there's only one path. There's only one equivalence class of homotopic path between those endpoints. But here you clearly see that's not the case. And this is sort of the beginning of how we're going to create an algebraic structure out of this in our next lesson, and how that is going to tell us something about the underlying nature of the topological space. Okay, so next time what we'll do is we'll actually turn this structure that we've got into a group, and then that group will be applied to our topological space, and then we'll study that in the terms of our Lie groups and our Lie algebras. All right, so see you next time.